the assignment because it's a good way of getting ready for the exam. And so I hope you did. So, okay, hold on a second. This we don't need. Okay, so here we go. So here we go. So guys, like if I give you this problem on a test, okay, where I'm going to give it to you, like you design it with the bolts the first time and you redesign it the second time. Well, this step you don't have to repeat, okay, because you've done it for the first one. It wouldn't change for the second one, okay? So I'm repeating the step here just to remind you what would be the minimum gross cross-sectional area of your angle, okay? But I mean, it doesn't change whether I'm doing it bolted or welded. This equation stays the same. The value of TF stays the same. Therefore, your AG will be the same. I hope you guys realize that. I'm just repeating it here so that we can see the value of AG that we would have got when we did the bolted side. Now here, the only reason
Sir,
yes.
I don't think you're recording.
Sorry?
I don't think you're
No, you
recording.
are.
No,
Yes.
No.
Yeah. Yes.
It's not recording. Hold on a second. Then
It is,
Sir. It is. It is.
Don't
recording.
mind Omar.
Okay, so I got two people say I'm recording. One person says I'm not recording, so I'll take the majority. No, just kidding. Okay, so let's go back to this. So I am recording. Okay, so what was I going to say? Now, guys, here the only reason I'm doing this, okay, is because when you guys, if I would let you leave this choice to you when you would go into the tables, right? When you go into the table, there are too many choices, and instead of me having to correct so many variable answers, I'm forcing you to pick what I think you should be picking as one of your choices. But in real life, okay, what you're looking for is you're looking in the tables, you're looking for something that is going to be in the vicinity of what you want to eventually design for. And therefore, now, here again, okay, last week we talked about this, okay, so keep in mind is that what's going to happen is this is this is going to be one of the angles. This is one of the angles. And basically, you'll only be able to weld here and here. So in other words, the outstanding leg here is only going to be welded along one side. And because of that, you will have a shear lag effect. And therefore, you have to account for that in the size of your member. And therefore, now, when it comes to welding, it's not as severe as when you're bolting. And therefore, I tend to increase it by 10% or 11% in this case, okay? And this seems to be good. And if I've underestimated my shear lag value, well, that's just a question of going back and doing another iteration. But this is a good starting point, okay? And like I said, this is a guesstimate. There's nothing in the books that tells me that I need to start with 0.9. I could have used 0.7 and I would have been that much more conservative. But this is a good point. This is a good guesstimate for shear lag for welding. And therefore, I will increase the angle size from 3333 now up to 3703, just to account for the fact that I have some shear lag. And therefore, if I go to, so I said a dash 89 by 7.9, 89 by 7.9. I'm looking for 3703. And of course, this is where you would 89 by 7.9. So 89 by 7.9. Oops, I shouldn't have done that. Okay, this is really big here. And so, oh yeah, this is good. So I would take 89 by 7.9 by 127. This would be a good angle here because I have about 3,300. I need about 3,700. I take that as a trial section. Let's see, that's what I mean. I should have done that. Yes.
Why don't we take the 152?
That's what I'm sorry. That's the one I picked. 152 by 89 by 7.7. That's the one I was looking at. Sorry. So that's the one I actually went for. The one that was very close to my value here, 152 by 89 by 7.9. Okay. The other one might have been too small. We'll see. We'll see once we calculate the resistance. We'll see if we were overly conservative or we were pretty close to what we needed. And of course, now what you want to do is you want to determine the size of the weld that you can provide. And of course, according to good practice, okay, because on an angle, you have that little fillet here, okay, because when they roll it, it ends up being rounded here. They recommend that you don't go over 75% the thickness here of the leg for your D, okay? This is your thickness, and therefore you simply, okay. Now, guys, 5.963 is a 6 millimeter weld, okay? Don't, so I mean, like, this is just good practice. It's not a requirement, okay? And I'm pretty sure like 0.07 millimeters won't make a difference when you're welding right along that edge there. So that's what you, okay, so therefore I will use a 6 millimeter weld. Okay, that would be the maximum one. If I want, I can even go down to 5. It's just that the smaller the weld size, the longer the weld segments. So now, here we go. So here I know that from my geometry, okay, this is established by the length of the leg, which was 152, okay? And of course, this is the line of action here. So what you have to always keep in mind is where's the TF force there, okay? What are the angles of the segments with respect to the line of actions? And also the resistance of the welds will depend on the angle with respect to the line of action. So that's what you always have to keep in mind. Now, here I know that, okay, here I know that this is the equation for VR, and you're more than welcome to use the equation if you know the value of XU, okay? And of course, XU is 490, because all these welds have an electrode strength of when you say 49 XX with electrode, that means it has an XU value of 490 megapascals. If you want, you can use the equations, but then again, if you do this, you're gonna have to check the base material to make sure you're doing it correctly. So I like to simply go, so here I go. So before I go to the tables, I look at two things. One is, okay, what's my line of action? Okay, what's the angle of my weld segment with my line of action? Here I know it's 90 degrees, and at the same size, what's the size of the weld that I want? And I know I want a 6 millimeter weld. So when I go to the table, I know what I'm going to be looking for, and therefore, so here I have a 6 millimeter weld, and the angle between the weld axis and the force direction is 90 degrees, okay, and therefore, okay, the VR value per millimeter, in other words, 1.21 kilonewtons per millimeter, that's going to be the VR value. So I have, and therefore I can action now. The only thing I have to calculate now, I'm doing this for, like I said, I have this value here. That's the actual length of the leg. The only thing I need to worry about is my M, because it's a weld group. In other words, because I have welds at different angles with respect to one another, it becomes a weld group. And therefore I have to calculate the MW value. Now, here is, okay, so remember, I mean, I'm going to repeat this a few times. Okay, so theta is the angle of the segment under consideration, and theta 1 and theta 2 is the segment that is closest to 90 degrees. So here, it's not only closest to 90 degrees, so in other words, the weld segment that is at 90 degrees is this one here, and therefore theta 2 remains theta 2 for everything else. So for example, if I had weld segments going like this, okay, the one that's at 90, that's theta 2, which would be the same for all these weld segments, okay? And therefore that doesn't change. So the theta, once you've established theta 2, it's the same for all the other ones. And of course, okay, and don't confuse theta here. Theta is for the line of action, okay? It's okay. So this is theta 1, the segment under consideration, and theta 2, the segment in the weld group that is closest to 90 degrees. And that always stays the same value for all the other weld segments. So now, of course, this is pretty redundant because they're one and the same. 90 divided by 90 gives me 1. Okay, so they're 85 divided by 0.85 gives me 1. So therefore, I know in this case here, this line segment is not affected by the weld group. Okay, and therefore I can calculate its full resistance. And now I go ahead and calculate what the VR, okay? Now always remember, okay? you have two angles, and therefore you have a segment on one side, you have a segment on the other side, and that would be the total value that both segments would provide for this connection. Now, of course, I don't remember what was the value of TF. Does anybody remember off the top of their head?
900.
900? That's what it was? Okay, 900. Therefore, we know that right away, the well segment here is going to give me, well, like 367.8 resistance here. Therefore, I can subtract that from this to determine what will be the length of this to give me a total value of TR greater than 900. So now what? Oh yeah. So what I'm doing now is I'm going to find the value of VR. Sorry. Now here, of course, you know, like you're going to try to keep the same thickness of weld. The only difference is that the other line segments are at 0 degrees. In other words, they are parallel to the line of action. So therefore, theta here is 0 degrees, and therefore this is the value of VR for those other segments. So this is the value of VR. Now I have two line segments, okay, I have 2 times this value here, I have 1 on each side here, and on top of that, okay, I have 2 angles. So therefore, in reality, by the time I'm finished welding these 2 angles together, I end up with 4 weld segments altogether. And of course here, this is where the value of MW changes, because the value of theta 1 here, theta 1 for this line segment here is 0. In other words, the same angle as with respect to the fourth, and therefore this becomes 0 here. And then theta 2 does not change. In other words, theta 2 is a segment that is closest to 90 degrees, and the fact is 90 degrees. And therefore, for these two, the value of those segments will drop slightly in this group, and therefore you use a value of 0.85 for each segment. And of course, so now that I've got the value of mu, I can now put everything in an equation, okay? And then I know that this is everything in terms of L2, just to be able to calculate the length I need here, because I have the value of kilonewtons per millimeter. I'm actually calculating the number of millimeters I'm going to be needed to get my total resistance. And of course, the total resistance is the resistance from the end weld here, and of course V2, and therefore I could go ahead, you know, one equation, one unknown, I can solve for, and of course the units work out perfectly. I end up in millimeters. Okay, so that means I'm doing the right thing. So that minus that, okay, divided by this value here of how much resistance I'm getting per millimeter weld because of the 4 segments, and therefore I end up with an L2 of 167.9. And like I said, guys, when you end up, like, even if I would end up with 160.3, okay, go to 170, okay? Don't round it down, round it up. Because when you're going to go to your gusset plate, it's going to help minimize the thickness of your gusset plate and so on. So always round up to a multiple of 10, okay? And therefore I will use here, okay, 170 millimeters. And of course, all 4 segments are going to have 170 millimeters. So like, don't be cheap. How can I mean, like, put more than less, because more resistance is always good in case you get an overload or a freak occurrence, better chance that it's going to survive that occurrence. So, now, so here we go. Now we're going to start calculating, for example, the value of TR based on the fact that we have some shear lag. And of course, calculate the TR for the shear lag. Now, here we know that TR is equal to phi u ANE FU, okay? And therefore that has to be greater than the effects of the the factor load. In this case, it's a tensile factor load of 900 kilonewtons, or force of 900 kilonewtons. Now, ANE, of course, is AN1 and AN3. Now, like I said, why don't I have AN2? Well, because I have a transverse weld here at the end, it eliminates my AN2, okay? And therefore and now, what I like to do is, okay, so it's, for me, to make it easier to calculate where the centroid is here. In other words, I simply take the length of this leg divided by 2 to calculate the centroid is. I will remove the thickness of the leg here, and only instead of doing this here and giving myself more trouble calculating where the AN2 is, I simply use this as my AN1 and use this as my AN3, just to make my calculation simpler. That's why I'm doing that, okay? And therefore, I know, for example, we said 152 by 89 by whatever it was, 7 point whatever, 7.9. And therefore, you know, like, it's much easier to go find the value of X bar if I do it this way. And that's why I break this into 2 different areas instead of worrying about the whole transverse area, you know, here. So that's why I'm doing that, just to make it my calculations a little bit easier. Now, of course, AN1 is 141.1, because this is just the thickness of the leg minus the width of this leg, and that gives me, and then, and now AN2, of course, okay, now, if you remember, when the length of the weld is longer than the width of the leg, okay, this is the equation you use. If all of a sudden the length of the weld is less than the width, you got to use the other equation. Okay, so this is the equation we use because we have 140, that's our L, and our W here is only 89. Therefore, this is the equation I can do to calculate AN3. And basically, of course, like I said, now, you know, I've seen people, like, you know, they take the centroid here, they take the centroid here, and since this here is, you know, sound like, so, and then of course this is a triangle, so you got to remember this is 1/3, and therefore the centroid of this weld here happens to be, if this is 6 millimeters, this is 2. Forget about that. Just keep your life simple. It's not going to make an iota of difference at the end of the day. Okay, we're not here to send a spaceship to Mars. We're here to build a building. And if I had to go to Mars and every ounce made a big payload difference, I would maybe get into that finesse. Understand? As a matter of fact, there's even fancier ways of calculating more accurately than what we're doing here today. So now we have 518.1. That's the value of AN3. Okay. So basically what this does, okay, it simply reduces the area, what it is, to a smaller area. So therefore it actually going to compensate for those whatchamacallit, concentrated stresses that are going to occur along the bottom leg, and until they become uniform, to compensate for that, you simply assume a smaller area to resist those forces. So now I have, okay, now remember, okay, so this is the total AN for one angle, this one and this one, and of course we need to have them for 2 angles, and therefore I multiply by 2. And the A and E, of course, has to always be less than. If ever you know, like, if you don't do this check here, okay, for example, if you would have said A and E, if A and E is equal to AN1, AN2, AN3, if you would have done it that way, you would have exceeded the 3,700 square millimeters of cross-sectional area here. And that doesn't make sense. How can you have more cross-section area than what's physically there? And that's why it's good to look at this all the time to see if you made a mistake in calculating your AN value. Okay, that's there more for a check, or for common sense tells you that your ANE value can never exceed your AG. You know, that's what they're saying. So now we have, so this is our equation, okay, and of course we use the FU value. Now, whether you're using 300 MPa steel or 350 MPa steel, the ultimate tensile strength is always 450. And since I like to work in kilonewtons, I will convert this right away to 0.45 kilonewtons per square millimeter. That's just so I can have the values. In other words, I divide right away by 1,000. And of course, this is the reduction factor. There's my area. And the TR value is 1,100. Okay, and wow, perfect. Okay, which is greater than the TF value of 900. Great. I know that it's sufficient. So the TR value of 1,118.8 is greater than 900. So therefore, I've compensated for that shear lag. So the angle is going to have enough area to overcome those temporary concentrated stresses until it becomes uniform again. Perfect. Now that I've done that, well, the last thing I need to do is calculate my gusset plate. And of course, what you're looking at here is that you're looking at, okay, that you're welding along here. You're welding along here, and you're welding along here. And therefore, if you're going to have a block shear, most likely this is the piece of metal that's going to shear out of your connection, and that's what you don't want to have. And you've seen that in the photo series last week. You can have block shear occurring, okay? So what you want to make sure is that and then what you have to look at when you're looking at your shear, what you need to remember, I'm going to repeat it here, is you have to look at what segments, you have to look at what segments are in tension and what segments are in shear, okay? So that's what you have to look at so you can realize, what you're calculating. Okay, so therefore, if the force is here, I know that's in shear, and that's in tension. Okay, and therefore, when I look at this equation here, okay, so in other words, AN, the very first one here is 152 because this is by T. And the one by G is, of course, 170 times 2 times T, because I have one on this side and one on that side. So, and then if you see that, you won't have problems realizing where these come from, okay? And of course, once you have that, this is the equation for TR, okay? And now, because you have a symmetric block shear, the efficiency factor here goes to 1. So that's 1 because it is a very symmetric block shear. And of course, this is the part that's in tension, okay, and you multiply that by FU. This is the part that's in shear, and therefore you put the value there in shear. And of course, don't make the mistake of calculating this, multiplying by 0.75 and adding that. That is wrong. You work everything in the brackets. I've seen that year after year. Okay, people are so messy that they calculate this, they multiply by 0.75, and then they add this to it. This also has to be reduced by 0.75. The whole resistance has to be reduced by 0.75, not just the tension side. And therefore, I end up with one equation, one unknown. And of course, now I can calculate the value of T, and I end up with 8.2 millimeters. And again, okay, when you go for your plates, okay, if you decide, let me clear this drawing, this is really messy, okay. So if you decide, okay, to not give them a second preference and you go right away to 10, then just put 10 millimeters. I will mark that right, okay. If you want to be a little bit more conscientious, because you need 8.2 and you have plates that are 9 millimeters, you can put on your drawing, 9 millimeters or 10 millimeters, and you leave it up to the guy. If you can find 9 millimeter plates, or if you don't even want to give him the choice, just put 10. You need 8.2. Is 10 bigger than 8.2? Great. So either decide to use always your first preference, but you want to show him that if he wants, and if he happens to have some 9 millimeter plate lying around in his yard and he wants to make his gusset plate with that and it's available, he's more than welcome to use it. So that's up to you. Okay, you're the designer. You choose. So last viewed. So like I said, if you want to tell him that he can go down as low as 9 millimeters, let him choose that. But your first preference, as far as you're concerned, your first preference of plate would be a 10 millimeter plate. And I think that's about it, right? And of course, you got to show everything on a sketch. So basically what you're showing here, okay, so this is, guys, remember the welding symbols, okay? So in other words, when the welding symbol is below, it's referring to the side that you're pointing at. So in other words, it's referring to this side, this side, this side, okay? That's number one, okay? Now, the reason why you don't put weld all around, because if you put weld all around, they would also have to weld here. This means welding all around. And you're not welding all around, okay? Because when you put the second angle, I don't know how you're going to be able to weld it all around when you put the second angle. There won't be room in there. Like you're asking the guy to perform miracles. So that's why we don't want to put the weld all around. And of course, you specify the angles that your connection is to be made with. Always specify the electrodes. In other words, in the table, they told you that those resistances were based on E490XX. XX, like I said, that's the specification of the electrode. The welder knows, for example, under certain temperature changes, whatever he is, you just worry about the resistance. Let the welder worry about what the XX value is for the conditions he's going to be doing the welding under. And therefore, so this is and then, like I said, the 49, unfortunately, like I like it in PSI because when you see E70 in period, when you see E70 XX, okay, this stands for 70 KSI, okay, kips per square inch, whereas here the 49 stands for not 49 megapascals, because that would be very weak, it's 490 MPa. Okay, that's the resistance, that's the XU value that you have in the equation, the strength of the electrode, okay? And of course, you specify the thickness of your gusset plate. And now guys, here, like I didn't show it, but in theory, this would also be welded, okay? If you want this thing to hold, right? But what we're looking at now is the detail. And of course, you would show the length of the segment here. And this would be 152. And of course, this would be somewhat redundant because you do show 152, but to tell him that he's putting to make sure that he puts the long leg, okay, not outstanding, it's the short leg that was outstanding. That's where you show the dimension here, because then he doesn't know whether he needs to put the 89 or the 152. And of course, in tension, I like to take advantage of getting as much transverse weld as possible. So I will put the long leg in this direction. In compression, I like to have more resistance because the further the material is the more resistance it is. In compression, I would put this in the other direction, okay? And that gives me more resistance for the angle. And that's it, I think. So let me just make sure. Yeah, before I go off, anybody have any questions? Before I end this, we're all good?
Yeah, no questions. Thank you.
Okay, so I'm going to I'm gonna close this. Yeah, I'm gonna close this. Okay, stop sharing. And now we'll get into today's lecture. Sorry, I hurt my hip on the weekend. I'm a little sore. Okay, now, guys, we're going to learn about well, I say bolted. It's bolted and welded, but they call it double angle connections. Okay, so let me just start from the beginning. We'll go slow, and hopefully we will not... I made a mistake. I forgot to fill up my coffee cup. Okay, so here we go. Double bolted angle connections. Okay, bolted, and I should have just called it double angle connection because it's not necessarily bolted. Okay. Now, here is the table. Okay. Now, let's look at this table together. Okay. So what do we mean by double angle connection? That means that on each side of the member that's being supported, okay, we are going to be placing an angle. So that's what we mean. And the reason why we want to have a double angle is that there are connections where you have what we call a single angle, but nobody in the industry uses that very much, because when there's a single angle, there's eccentricity, and that becomes, so people like to use double angle connections this way, that there's no eccentricity in the connection, and it's much easier to calculate the values. So that's why everybody likes to use double angle connection. And like I said, this is the most current way of when you're connecting beams to columns or beams to beams and so on and so on. This is the most current way of making the connection. Okay, so now here, the way that the table, let's talk about how the table is divided. Okay, so this side here is when you're going to be bolting. This side here is when you're going to be welding. Okay, so that's the only difference. Is that so here I decide to put bolts, here I decide to put welds. Now, here is, let's talk about the bolted. Now, this is when you want to bolt the supported member, or you want to bolt the supporting member. Now they say supporting because the supporting member can be a column, can be a girder, could be whatever you want, okay? So whenever I refer to the supported member, okay, so here when you see the word supported, okay, beam, they're looking at the member that's being supported, and whatever, in other words, if I look in plan view, what's the member that's holding up without having it fall down? That would be, and then what, and so on. And so that's the supported member. Now here, this is the more typical one where you bolt the supported member, okay, and so on. And of course, what they show you here, let me just clear this drawing because it's starting to be a little messy. Okay, what they're showing you here is, for example, G1. Okay, if you want to know the gauge of that, these are the suggested gauges depending on the size of the angle. Okay, so in other words, they start with a 3-inch angle and they move up to 3.5 inch and 4 inch. So in other words, the angle sizes that we normally use for double angle connection are 3 inch, 3.5, or 4 inches. Okay, so G1 is the distance from the back, from the side, from the back side of this leg here to where the first line of bolts are going to be applying. So that tells you what. And then of course, for the supporting, this is the gauge distance between the line of bolts, and this is what's recommended. So this way, when you put them down, it will not interfere with that little fillet inside the, like when you put your washer down and you put your bolt down, you want to make sure you're far enough so you're on the flat part of the leg and so on. So this is just to give you, more information on how to detail your connection. Now here, what they do is they have minimum and maximum sizes. Okay, so for example, if your beam happens to be a W250, well, you should be looking in this range. Okay, if your beam is a W200, you should definitely be looking at this one. Okay. Okay, so because you need a minimum of 200 to use it. So in other words, if you have a table that you're using a beam of W150 by something, well, you can't use this table. You can use a table for certain reasons, but you're going to have to work out a lot of the geometry for yourself. Now, so it tells you the beam size, the nominal depth of the beam size. And then of course, once you have this range, L is going to be the length of this angle here. Okay, some people like to call this clip angles, and some people like their clip angles, and some people like to call them angles. I just call them angles. Okay, and of course, when you have a beam that varies from 8 inches to 12 inches, okay, this is what this is. Okay, the angle length would be 6 inches, and of course, in there you would put a maximum of 2 bolts in a vertical line. So, because here you notice that they have an end distance of 35, an end distance of 35, and they have a gauge distance, okay, of 80 millimeters, okay, which is, like I said, we used to use an inch and a half, an inch and a half, and 3 inches. And what they did here, instead of having 76, they rounded it up to 80 for metric, okay, and multiples of 10. And here they use multiples of 5, okay, as opposed to, so that's what this is. Now, here, what you're looking at is bearing type connections, which is what we've been doing so far. Okay, this tells you the bolt size. So you'll notice that the more typical size that they have is a 3/4 inch bolt is what you use to make connections with. And of course, if you like I said, we'll be doing both just for exercise purposes. But if I was doing a real connection, I would always be using a 3/4 inch bolt. Okay, and then if this is not sufficient, I would go up to a 7/8 inch bolt. Okay, so these are the two bolt sizes that and then on top of that, it's an A325 bolt. It's not an A490. Okay, so therefore, this is the most typical high strength bolt that we use. That's number one. And of course, if I have 2 bolts and the threads are intercepted, then this gives me the shear resistance of what those 2 bolts will provide when I do the connection. So when I'm looking for my VR value and I know that my threads are going to be intercepted, I come here. So I'm going to be using 2 bolts, okay? And I use a 3/4 inch bolt. And therefore, if I want to know what the VR is for that, well, 316 kilonewtons, okay? Now, you'll notice that for 3 bolts, okay, for 2 bolts, I get 316 kilonewtons. And it makes no difference whether I put him here or if I put him, now here it looks like I have 6 bolts. You agree? Okay. But believe it or not, the value in the table here is the same as the value in the table there. Can somebody tell me why?
I'm sorry, it's very small, so it's hard to read.
Oh, it's very hard, very small. I apologize. Well, like this, I wanted to show this side by side, so I had no choice but to put it like this. Okay. As a matter of fact, in the book, you open them. One is on one page, one's on the other page. But what I'm trying to ask you is that why can't okay, like why is it that if I have 3 bolts here, my VR value is 316, and when I have 6 bolts here, my VR value is 316. Why is it one and the same? Should this one be twice the amount of this one because I have 6 bolts in this case?
Isn't because it's just like two single, like on the single angles, there's 3 bolts.
No, but here, like in plan view, I have an angle like this, because like here, this is the angle like this, okay? And then I have the angle like this, okay? And therefore, I have this here is this leg here, okay? And so I still have, like, in other words, I have 3 bolts here, and I have 6 bolts here, but yet in the table, the VR value is exactly the same. Does anybody realize why? Would anybody want to venture a guess? Nobody has any idea why we have exactly the same value for 3 bolts and 6 bolts. Shouldn't the 6 bolts give me twice the value of the 3 bolts?
Is it because there's more holes inside? That's why it's not so it's the same strength.
This one, like, don't forget, like, in other words, this is going to be the connection here. So in other words, this is I'm using 3 bolts to support the beam, okay, and then here I'm using 6 bolts to connect it either to another beam or to another column or a column, okay?
Is it because it's symmetrical?
Sorry?
Is it because it's symmetrical?
Well, I mean, this is pretty symmetrical to me. There's one line of
I
symmetry
mean,
here.
they have the same line of action basically.
Hmm.
You know what I mean? Like they are in the same line. It's like the whole 2 bolts are in the same line, and
Okay, so here, like for example, let's look at this line here. Okay, let's look at 3 bolts because that's what you see in the diagram. People tend to, here they're just showing you graphically where the bolts are located. Okay, so let's use this one so people can graphically relate to the number of bolts. So here I have 3 bolts this way. I have a VR value of 474.4. Here I have 6 bolts this way, and I have a VR value of 474.4. 474. So I have the same VR value because both diagrams apply to this table.
Because the same amount of bolts on vertical line.
Like I'm using, to make this connection here, if I was using a bolted connection, I would end up using 9 bolts. You understand? In other words, if I was be bolting to the supporting member, if I be bolting to the supported member, I would have a total of 9 bolts in my connection.
I didn't
I'm
understand.
not sure what you mean.
Yeah, no, me neither.
Pardon?
I'm not sure what you mean. We have like 9 bolts.
no,
I mean,
yeah,
I have 3 bolts here to connect the beam to this angle. And then I have 6 bolts here to connect the angles to the column. In other words, if I had a column here like this, right? Well, I would have here, I would need to put these angles here, and I would have 1, 2, 3, and then I'd put another angle here. So this connects the angles to the column. So I have 6 bolts there. And when I look at the beam that's going to come and be supported there, I have 1, 2, 3 bolts there. So I have a total of 9 bolts to do this connection. Don't you realize that?
Okay, but it still did not answer why we have the same VR for 6 volts on.
Well, it doesn't answer it, but I'm asking you, why do you think it has the same VR? I'm seeing if anybody can think of why it has the same VR value. It's not a trick question, guys. Trust me.
Can you give us like a hint? Because it seems that.
How many shear planes do you have here in this connection?
3.
On this side, I have, like, you guys might not see it, but the bolt is going right across here like this to be able to connect it. You understand that this is where this bolt here is going right across here. So I have one. So here the bolts have double shear, and here the bolts have single shear. So therefore, it's the number of shear planes. Because they have the exactly same number of shear planes, I had the same number of VR. Okay. Now, this table here, of course, gives you the VR value for the number of bolts, but you have to be careful. In order for you to use the values here, you have to come down here and make sure you check all these requirements down here. And we will be doing that in the example. Okay. So this side here is when you're going to be bolting. And this side here is when you're going to be welding. Okay. Now, the common thing to do is to weld to your supporting member and then to bolt to your supported member. Or you can weld to the supported member and bolt to the supporting member, but you never weld. That you don't do. Or you can bolt, you can bolt weld, but you never weld because you don't want to weld in the field, okay? So that's something you should keep in mind. And I came up with 3 examples where we're going to have like the typical one where we weld to the supporting member and bolt to the supported member, and then we're going to switch it around, and then I'm going to have one where I'm going to be bolting, and I'm going to have 3 examples so you guys can relate to this, okay? But you never weld. You always either bolt, weld, and which one do you bolt and which one do you weld? Typically, the supported member is the one that gets bolted, and the supporting member here, because the supporting member would be right here, okay? And therefore, these in order for you to use the values here, they have to have the values that you have here at the bottom of the table, and we will check this as we go along to make sure that we meet these requirements, and so on and so on, and therefore and so forth. Now, so like I said, this side is the bolted side. Oops. This side is a bolted side, and now this side is a welded side. Now, once you have determined that if you're going to be bolting and welding, okay, once you have determined the number of bolts you need, for example, if I decided that I need 4 bolts here, okay, and my angle here is 310, well, you don't go on this side here and you take an angle that's 390 and you take a VR value. You have to be consistent. You have to stay on this side, and then you have to look at these values to determine the size of your weld. Okay, so you can't say I need 550 on this side and I need 790 on that side. That doesn't work. So whatever you do on one side here, if I start with the weld first and I decide here, and then I want to go look at the bolts, well, I have to be consistent. I have to always stay on the same side to see how many bolts I need on that side. In other words, that's why they tell you here, what is the size of the angle? Okay, what is the size of the angle, so that when you come to this side of the table, you make sure you're on the same row. Okay. And that's the thing. Now, excuse me, clear. Okay, so that's just, we're going to be using this table for a couple of examples, and you guys are going to have to use this table, you know, for your project and so on. So this is just to give you an overview of how the table works, and we will get into these details of these minimum values. Okay, so now, okay, so at the bottom of each table are the values of the minimum material thickness required to develop the capacity listed in the columns. Okay, so in other words, if you don't have those capacities, you can prorate. Okay, you can prorate the values either in the tables or the material thickness that you have. Okay, so for material thicknesses less than those listed, the capacities may be reduced by the ratio of material supplied by material thickness. So for example, if I'm using a 6.5 millimeter web thickness and they recommend that you have 7.7, well, I take 6.5 divided by 7.7, I take the value in the table, and that becomes my VR value. Okay, and then the converse also happens. If I have something thicker, then I can reduce the material that's listed. And we'll do this in the example. Now, here is, for example, how you design connections, okay? Now, these are called beam load tables. I only have one here. I will send you a file at the end of the, at the end of the lecture. I will send you, in the file folder, you will have all the beam load tables for all the different beam sizes, okay? Now this is just one, okay? Now the way that, so for example, if I look at a drawing, okay, so for example, here is a drawing, okay, here's a column, and what the structural engineer does is this, okay, here I have a W 530 by, let's say 76, okay, 76. And he gives you that the span here, from here to here, is 4 meters, okay? So what did he design the connection for? Now, some people will tell you what the shear force is here for the beam, and some don't, okay? So some drawings are done better than others, but if you don't see the shear force there, then you can reasonably assume that this beam is going to be have a maximum uniform distributed load acting across it. And what these tables here gives you the maximum load that you can apply to the beam based on the fact that the beam is going to fail in bending before it fails in shear. So for example, if I have a W5 30 by 74 and it's got a 4 meter span, the maximum load that this beam can carry is 1,220 kilonewtons. So that's where I get my VF value from these tables. So I don't have to call up the engineer or anything, or the guy that did, okay? If I want to design this connection, I can just say, okay, this is the designation, this is the span. There's nothing, if he doesn't put a specific VF value because there's something unusual, then I have the right to assume that it's just uniformly distributed, and this will become the maximum load that the beam will carry. So therefore, if I look at this beam here, that's the maximum load that comes down of 1,120 kilonewtons. Well, I know that if I have two connections, well, I can assume half will go there and half will go there, and therefore this will be 1,120 divided by 2, and I will design my connection for that force. And these are beam load tables, and I'm going to send you a copy of all the, like for example, starting from a W1, like from the biggest size to the smallest size, I will give you a copy of that. Okay, so this is where you get the value of VF. Okay, so if it's not specified in the drawing, what the engineer wants you to design the connection for, it's safe for you to come to these beam load tables and get the value and find your value of VF. So that's what these are. And of course, we'll be using these. Okay, so here, okay, so now let's apply this to an example. Okay, now, first of all, design a double angle bearing type connection for a W530 by 92. Okay, so that's the beam. Okay, so like in other words, I would be looking at a drawing. I would see here in plan view that this is a W530 by 92. Okay, okay, this is the grade of steel, of course, that is simply supported with a span of 5.5 meters. So this gives me the span here. I have 5.5 meters. And here, there's nothing indicating what the shear force is on the drawing. Some people put it on, some people don't. Now, the angles are to be bolted to the beam web. So what you want to do is that here's my beam, like this, okay? So on this side, I will be bolting the beam, okay? And then, okay, and then on the column side here, okay, this is the column. In other words, here, like if I'm looking in this view here, okay, this is the elevation, okay, I am going to be welding the two angles on the column, okay, so that this will, and this is going to be welded here, okay, and so I'm welding these two angles, so this will be all done in the shop, and then in the field they will come and they will be able to slip this in here and then bolt it together, and the whole thing gets erected, okay. And like I said, this is one of the more typical, okay. Now, the threads of the bolts are to be included in the shear plane, so therefore I'm going to be conservative. I'm going to take the lesser of the VR value. Okay, I'm going to use a W76. So I'm giving you a W76. I'm also trying to, you know, steer you, okay. In this case here, like I said, if I was doing this, I would use 3/4 inch bolt. I wouldn't use M20, but I'm doing M20 so that you guys can realize that, you know, where you get the value from the table. Now, A325 bolts is what the table is based on. So therefore, in your specification, you're going to have to say that you have A325M bolts because I'm using metric, okay? And of course, this is the steel for my angles, okay? And if you look at the bottom of the table, it says make sure that your angles have a minimum strength of 300. And of course, E49XX electrodes, because the table is also based on the E49XX electrodes. And of course, I want to show me your results on a sketch, because I want you to be able to sketch this. So now, so the first thing I need to do is, of course, go look at some information I'm going to need to verify the values in the table. So one of the first things I'm going to do is I'm going to go look for the W530 by 92. Okay. And I'm going to go look for 5W by 92 because what I'm really interested in is the thickness of the web, because this is going to tell me what is the thickness of the material required for the connection to work. And therefore here I have a thickness of, a thickness of 10.2 millimeters. So that's where I get the thickness of my web. So I need to know W, the thickness of the web. So I go for the web thickness of 10.2 millimeters, okay? Now, I also need to know the thickness of the flanges of the column because I want to make sure that they meet the minimum requirement according to the table. So I will go and I will also look at a W250 by 73. The thickness of the columns is 14.2 here, okay? And of course, the other thing I might be interested in seeing right now, because I want to make sure everything works, is this value here, 192, okay? So this way, at the end of the day, I want to make sure that I have enough width here to be able to put those two angles, okay? So like in plan view, here's my column. I will be putting an angle here like this. I will be putting an angle here like this. And I want to make sure that at the end of the day, whatever this dimension here is less than this dimension here. Because if it isn't, I'm going to have to modify and cut the legs a bit for it to fit, okay, if I'm welding there. So that's something you should keep in mind, okay? So last view, okay. So therefore I have the column flange thickness is 14.2, which is a nice thickness, by the way, okay? And then after that, now, I want to know what is going to be the force I have to design this beam for. Of course, like I said, I don't have the VF force indicated on the drawing. So I'm going to go, so this is a W530 by 92 with a span of 5.5 meters. So that's the information I need to have with me when I go to the beam load tables. So here, so I'm here, 530 by 92. In other words, this is the nominal depth. This is the mass per unit length of, 92 kilograms per meter. And I have a span of 5.5 meters. In other words, 5,500 millimeters, okay? Now, if you happen to have a span between, like, let's say it was 5,725 millimeters, okay, then be conservative. Don't interpolate. You can interpolate, but just go take the higher value. you know, so always go to the smaller span because you should always take the higher value. So right now here I have, so the total uniform distributed factor loads, okay, in kilonewtons. So in other words, this tells you that these values were based on your beam having a total uniformly distributed load going right across it, even if they're concentrated, doesn't matter. And the beam was based on, the beam capacity was based on the maximum bending of a fully laterally supported. So in other words, the maximum MR value, and based on that maximum MR value, they gave you what the VF value is here, okay? And that's what they did. So here I have 1070 kilonewtons is the maximum load that I can put on this beam, or this beam should be designed for according to this table. And if, of course, if the beam is undersized, and that's not your problem, well, I mean, it can be your problem, but anyways. So that's it. Now I come here, I have 1000, like I said, for this one I have, for 92, I have 1070 kilonewtons. So I have here, the total factor load is 170 kilonewtons. Now you got to remember, okay, that's the total load coming down on the beam, okay? And therefore you can assume that half will go to one connection and half will go to the other connection. Therefore my VF value here is this divided by 2. In other words, I have, okay? And so therefore I don't design for this. If you design for that, don't worry, you just design it for twice what it actually has to carry. So it's only going to be twice safer than it has to, and then some, okay? So that's the, so I have, so in other words, the shear force I have to design for, the VF force, is 535 kilonewtons. So now I know I want to use, like I said, I'm forcing you to use a 76 millimeter, okay? So I know I have a beam that has a depth of 530 millimeter, a nominal depth, and I want to have a VR force that's going to be greater than 535 kilonewtons. And I know in this case that I'm going to assume that the bolts, the threads are going to be intercepted. So I'm going to go back to that diagram here, and we're going to take it slow, okay? So here are, okay, so we said we're going to be using M20 bolts. That's number 1, okay? We said that we are going to be having threads included. That's number 2. So I am on this side, okay? I am on this side, okay? I'm looking here. And after that, all I'm looking for is a VR value that is greater than 500 and, what was it, 525? I don't remember.
The BR is 535.
535. Is that it?
Yeah.
Okay, so is this any good?
It's too low.
Too low, exactly. So therefore we should go here, okay? Now, in other words, my VR value is 701. I need 535. Perfect. Okay. Now here I look, does my beam fall within this range? Yes. In other words, my beam is a 530. Okay. So I know that my beam falls within the range where I can actually stick this angle. So therefore the length of the angle is going to be 310 millimeters. So this is going to be 310 millimeters, and I'm going to have 4 bolts. I'll be able to put 4 bolts in one line, okay? Then of course, once I've decided this here, when I'm going to go look at my welding of this to I know that I'm going to be looking right across where I still have the same length, and then I'm going to come back and choose what I need here, okay? Choose what I need here to, I should be down here because I said to use a 76, so I apologize. Okay, so, sorry. So therefore, that's where I get the number of bolts I need, and I get the length of the angle that I need. Okay, now I'm going to come back to this because I want you not to get confused. Okay, I'm going to come back to this. Oops, sorry, I shouldn't have done that. I apologize. Okay, so here we go. We have a vertical line with 4 M20 bolts, threads included, provides a capacity of 701, and it's greater than my VF value. Okay, now the only thing I need to do is, in order for me to use this value in the table, I have to go check the material thickness. Okay, so check the web thickness based on bearing. Okay, so the reason why they give you those minimum thicknesses to make sure you have enough bearing and so on. The required thickness of the framing angles for the steel. Okay, now I went up to 701, but I only need 535. So therefore, I don't need what's in the table. I can actually, okay, so I come here and I go look, okay, and I say, okay, this is what I've decided to use, 701 here. Okay, if I go to the bottom, okay, it says minimum required web thickness of supporting beam is 8.1 millimeters. So if I have at least 8.1 millimeters, I can rely on the fact that it's going to have a value of VR of 701. Okay, so that's where I get that. That's what that means. Okay, so now what I'm actually going to do is that 801, okay, that 801 was going to give me a value of 701, but I really only need 535. So I can go down as low as 6.2 millimeters. So if ever I have a beam that, like for example, I go to the table and I have a web thickness of 7.8, and I do this ratio here of what is required versus what is provided, I have 602. Here it seems a little redundant because I already have a thickness greater than 10.1, but I want to do this to show you that you can always do this little calculation, see what you actually need, okay, in terms of material thickness for the strength that you are actually going to have to resist, okay? So here I have 10.2, I need 6.2. I know I have sufficient web thickness for me to be, as a matter of fact, because I have 10.2 and I need a minimum of 8.1, I will be guaranteed to have that value, that much resistance. But if I don't need to go that high, I can actually go down to a thickness as low as 6.2, and that will give me a value of 535. So that's, so now we check the web. Now, the minimum thickness of angles, okay, so we'll go back here, okay. Here what they're saying is, I was here, okay. So here, the minimum required thickness of framing angles. So in order for the framing angles to be able to provide the bearing required for my connection, I need a minimum of 7.7 millimeters of thickness. That's what I need in terms of the angle. So this, the top one was for the web, the bottom one was for the angles. Okay, now I do the same thing. So here I said, well, I need 7.7 in order to have a resistance of 701, but I don't need 701. I need a maximum resistance of 535, and therefore I can reduce the thickness of my angles down to 5.9 millimeters. And that's what's nice about it. So instead of going up, I can actually choose an angle that's going to be slightly thinner, and I'll be able to get the resistance I need from that thinner angle. So that's why I do this ratio here, okay, versus what I need, what I can get based on the thickness that's in the table, and therefore to get this resistance here, I can go down as low as 5.9. So that's for the angles. Now I'm not there yet. I'm just going to check to see on the other side what size of weld I'm going to need, and then that's going to determine the thickness of the angle. And then from there, I'll make sure I have at least this value here so that I also satisfy the bolted side of my connection. So now the minimum length was 310, 4 bolts, and the beam is 530, okay? Now for the outstanding legs to be welded, okay, I go to slide 16, okay? So this is the outstanding legs. These are the being welded here. Now, I want to stress this, okay? When you're welding these angles, okay, you put a full length of weld here, but the return here and the return here is only 2 times the diameter, 2 times the thickness of your weld. So in other words, if I'm using a 10 millimeter weld, this would be a maximum of 20 millimeters return. And you do not weld all the way across here. That's a no-no. You just weld a small return at the very top, and you don't necessarily weld at the bottom here, okay? And the reason why you do that is because you want the angles to be flexible and be able to, you know, bend outwards so that you can get what we call a simply supported connection. Otherwise, your analysis would be off. So here we are. This is the angle we want to use. We said we had a 310, and we're looking for a VR that's at least 525, and therefore, if I use a 6 millimeter weld, I do end up getting a VR of 568, okay? And therefore, all I need is a 6 millimeter weld, and I will get my VR value, okay? So that's where I find the value of my the weld size, okay, based on, you know, like here we had 310. Okay, so this once we took this geometry, I take that geometry and I bring it to this side. And then once I decide that this is going to be the size of the angle, well, then I use this part of the table, because if I was going to use an 89, I would use the upper one. And I go look for a VR value that's greater than my VF. I hit one right here and I go up and I see that a 6 millimeter weld will be sufficient to give me at least 535 millimeters of resistance. So last viewed. So there's my VR value that I got from the table, greater than my VF value, and that's for a 6 millimeter weld. Now we know that the minimum thickness of weld, of angle, okay? We know that we are going to be welding, okay, again, because of the good practice, we know that we are going to be welding where there's a fillet, okay? And if this is 6 millimeters here, we know that this should be at least, you know, one, and like in other words, this could be a maximum of 0.75 T, and therefore D should be equal to 0.75 T. Okay, so therefore I will divide this by 0.75 to know what thickness this has to be in order for me to be able to make that weld nicely there. So D should be less than 0.75 T. And now I have a 6 millimeter weld. Well, I'm going to have to use a T that's at least 8 millimeters thick. Okay. Now, there, like if you go to the table, you know you're using a 76 by 76. So therefore, 76 by 76. You come here, and you notice that the standard thicknesses are you have, okay, 3/16, 1/4, 5/16. Okay, so therefore you do, like, guys, this is, in all intents and purposes, this is 8 millimeters. 7.9 is 8 millimeters, and therefore I know that this is a good one to choose. I need 8. 7.9 is 8 for me, at least it is. Some people know. Some people might have gone up to 9.5. I don't recommend you do that because you want to keep your angles as flexible as possible. So 7.9, 8 for me, 0.1 millimeters is not going to make a big difference. And as like I said, that was for welding, good practice. So that's the one I'm going to choose. So therefore, I'm going to choose a 76 by 76 by 7.9. Now, if you remember, when we did, before we did the minimum thickness of angles for the bolted side is 5.9. We have 7.9, so we have no problems. It's going to give us sufficient bearing so that we don't have any problems when the bolts are going to be sitting on the angle. So we've checked that before. We checked what was the minimum required here. And this, of course, 7.9 ended up being determined by good practice. In other words, making sure that the size of the weld is no more than 3/4 of the thickness of your leg. And that's how this got determined. Now, flange thickness of supporting columns, okay? So we come here and we look at what they want, okay? So this is the size of weld we have here, and here it says minimum thickness of supporting material with beam framed on one side. And that's exactly what we have, okay? So in other words, here's our column. Here's our angles like this. Okay, our column is here. Here's our angles like this. Okay, and we're only framing on one side here, so therefore they want to make sure that you have enough material here so that that weld is going to be, and of course your beam is going to be in here somewhere with those 3 bolts, and therefore the minimum thickness of supporting, okay, so right here you need a minimum thickness of 4.6 millimeters. Now, of course, this was the resistance that we, okay, this is the resistance that we needed. If I put at least 4.6 millimeters, this is the resistance that I'm going to achieve. I can actually bring that down a bit. I can go down to 4.3. I know that the flange thickness is 14.2 millimeters, absolutely no problem. Okay, so therefore, I will definitely be able to rely on the higher value. And like I said, I'm doing this so you keep in mind that sometimes you end up getting your web thickness requirement is greater than what's smaller than what's in the table. And I'm just showing you how you can prorate to see if you're still okay with the values in the table. So those values at the bottom of the table, like I said, these values here, okay. Okay, so all these values here that you have here at the bottom of the table is just to assure you that whatever you take from the tables here, okay, all these VR values that you take from the tables here are adequate, making sure that you have at least this, in other words, this thickness will guarantee me all these VR values. Now, if I happen to have something smaller than 3.8, I happen to have 3.2, then I can take 3.2 divided by 3.8, and I can take the values in the table and reduce them and see if I still have enough. Or the other way around is if I have more, then I can actually reduce the thickness that's required to give me the values in the table. And that's what I'm doing. Now that that's done, of course, what you need to do is show everything on a sketch, okay? So basically, now, when you're showing your stuff on a sketch, I want you to notice a couple of things, okay? So your column would be here, guys. I don't know if you see this, but your column would be right here. The flange of your column would be right here, okay? And the flange of the column, and then the welding would be right along here, along this side. In other words, this weld would be there. So here what you're showing is, that this is a side of the beam that's going to get bolted, okay? And I want you to look at what we did here, okay? So in other words, you cooped the beam. And the reason why you coop the beam is because in plan view, when you're going to be erecting your steel, here's your column, okay? And the beam is going to have to drop. And of course, here's your angle, and here's your angle. Here's your angle, and here's your angle. So if you do not coop the bottom, you'll never be able to drop the beam in between these two angles. So we coop the beam so that when they lower the beam into its place, this flange will not interfere with these angles because the angles will already be there welded to your columns, okay? And they're going to be fairly straight, the columns. And if you notice that when you, like for example, whatever the dimension is from column to column, okay? You always make the beam on both sides 10 millimeters shorter than what you actually need in the site, okay? And that's to help for erection. So this is called a coop beam, okay? And now you can appreciate why when we were taking the values of VR from the table and we were sizing the beam, well, you're removing some of the web here, you're removing some of the web here, you're removing some of the web here. So therefore, in reality, you are having less VR, and therefore, by taking only 80% of the VR value, you kind of assure yourself when you come to detailing your connection, you won't run into a problem. Because in theory, if you use a table and you respect all of these dimensions, in theory, and all the minimum thicknesses, you shouldn't have a problem, okay? But if all of a sudden you're not using the tables and you want to do this like with you have to calculate the fact that this thing can shear off and so on, okay? So that's the side that's going to be bolted, okay? And therefore, like I said, this is the cooped side of the beam, okay? You coop it so that you can lower the beam in between these two angles. So in other words, the beam would eventually, okay, the beam will eventually get lowered in between these two angles like this, okay? So here's the beam that gets lowered into the in between these two angles, and therefore, if you do not cut this part of it, you'll never be able to fit it between these two legs, okay? And of course, this is important, okay? The distance, the gap that you leave here, okay? It cannot be, first of all, it has to be at least the width of your web. In other words, if the web is 10.4 millimeters thick, it has to be at least 10.4, otherwise it won't fit, number one. And number two, what we normally do is we take the web thickness and we add 2 millimeters. So if our web thickness is 10.4, I would specify at least a 12 millimeter gap here. I wouldn't worry about 0.6, 0.4 millimeters, okay? So that's how you specify the gap here. And I want to see this on your drawings. I want to see this in your exam. In other words, I don't want to see web thickness plus 2 millimeters. You tell me what the web thickness is, 10.4 plus 2. So if I see 12, I will mark it correctly. If I see 13, I will mark it correctly. If I see 14, I will mark it incorrectly, okay? So, because if they're too far apart, like in other words, if your gap is too far apart like this, okay? If your gap is too far apart, okay? When they're gonna come and bolt here, you're gonna be prying those legs together, and you're gonna be causing additional stresses here on these angles, which you don't want to add into your design, okay? So that's why the gap is very important. So in other words, 2 millimeters is enough for them to be able to slip it in. If you want to be more generous, like you can go up to 1/8 of an inch, 3 millimeters, you understand? But 2 millimeters minimum that you should be specifying here, maximum 3 millimeters, okay, 1/8 of an inch, and that's the maximum gap. And on top of that, okay, the return should only be 2D. So therefore, the return here is 12 millimeters. 12. So this way, the connection stays flexible, and when the beam wants to rotate, this is what happens in plan view. So here's my column. Okay, here's my angle that's attached here. And then what happens is that it stays, the angle actually flexes out for the rotation and it doesn't create secondary stresses because you weld it right across here, okay? I should have gotten you a picture to show you how this thing actually flexes out under its rotation. And that's it. And then of course, the other thing is, so this is your geometry. And then of course, you're using G40 steel, 300W for your steel, okay? And of course, these are the electrodes. You have to specify what electrodes to use because that's what the table is based on. This is the size of the angles that you're using, okay? And of course, you have to specify that you are using A325 bolts, and they don't care whether it's threads included or threads excluded. You've calculated with the threads included, so if the guy happens to be using shorter bolts, you don't care. If ever you specify that you don't want the threads to be included, then you should specify here threads, and the guy's going to make sure that when he buys his bolts, that the threads are going to be outside of the shear planes. Okay, that's all. That's the only difference. Okay, so if you're going to be designing based on threads excluded because it's going to give you a higher resistance because that's what you need, make sure you specify on your drawing threads excluded. Okay, or non-intercepted. And that's it. So that's the first example I have for you. Does anybody have any questions before I move on?
Not at the moment.
No. Okay. So now the second one is going to be very similar. Okay, I'm going to go a little bit faster because it's going to be like the same thing, except that here I am. I'm telling you, design a double angle bearing type connection for a W610 by 101. Okay, that is simply supported with a span of 5 meters. Okay, so 610, 101, 5 meters span. Okay, welded to the, oh yeah, last thing I want to say. Okay, now the only thing you have to be careful about, okay, is since you are welding this, since you are welding this to a column, okay, sorry, you know, like your column here has a width B, okay, and if this is what you're doing, make sure that the dimension from here to here, make sure that it fits in your B. Otherwise, you're gonna, you're gonna have a problem. So that's something that you should take into consideration. Now, okay, now the threads of the bolts are to be included in the shear plane because I like to be conservative. So this way I get a little bit more bolts. I really don't care. Again, I'm going to use a W76 3/4 inch A325 bolts. Okay, and this of course is so I make sure that I can use the values in the table because I'm using the same electrode strength and the same strength of bolt as the table is. I'm not going to use A490 because it's a different value. So now, again, I'm first going to look at the geometry or the thickness of the materials for this beam W610 by 101. W610 by 101, I go get the value of, so it's very important I have the web thickness because that's one of the materials that I have to check. And at the same time, so I have a W of, the web thickness is 10.5. Now, the web thickness is 10.5 millimeters. Now, the column thickness. So I am welding it. In other words, what's happening here is I have to be careful again. Okay, so what's happening here? This is my column, like this. And I'm going to be welding it in here, like this. Okay. So I have to make sure the whole thing fits between these two flanges and so on. Or I'm going to be bolting it in there, I should say. Okay. So now, okay, I should have gone here to show you. You know, you guys know where to find the web thickness. So therefore, and at the same time, I'm going to be looking at this here. Okay, this is something you should keep in mind, the value of T, because that's the value that you have where it's all flat in here. That's the T value. Okay, so if I'm going to be bolting some angles in here, when I end up finishing my geometry, I want to make sure that this whole thing can fit in between those two flanges, and I want to make sure I'm always on the flat part of the web, and that's what the T value tells me. So now, oh, I should have done that. Sorry. Okay, so there we go, 6.4, and like I said, the T value, I didn't write it down, but that's something you should take into consideration. Now, here I go get, it's a W610 by, we said 101 with a 5-meter span. Is that what it is? Yeah, so 610, 101. So here we are, we're at the 610, we're at the 101. So we're here, and all I have to worry about now is my span of 5 meters. So there is a maximum load that that beam should carry, and therefore that's what I will be designing the connection for. And so therefore that's what I'm going to be doing. So there we go. We have a total factor load of 1,440 kilonewton. And of course, we know that half goes to one side, half goes to the other side. So the connection will actually be designed for 720 kilonewtons. And we said that we are going to be welding it to the beam. We're going to be welding to the beam. And of course, we're going to be bolting it to the column. I mean, I just did this so that we can get the practice of using both sides of the table. So now, I'm going to be welding it to the beam. So what am I doing? I'm actually welding my angles to the beam. Okay, so therefore I'll be using this side of the table. And on top of that, I'll be using a 76. I told you to use a 76, okay? And now the only thing I have to worry about is, of course, the, you know, like the beam size. It can go from, okay, where we want to go from. And so therefore, we're looking for a VR value. Somebody find a VR value that's greater than our VF value. Can anybody see one? Well, right here, I have a VF for a 5-millimeter weld. I have a VR value of 782, which is greater than our VF value of 720, I believe it was. Yeah, 720. And this would be for a beam size that is somewhere between minimum, I'm sorry, this would be a beam size that's somewhere between 460 and 760. We are at 610, so that's good. And therefore that establishes the length of our angle. And then of course, when I come to this side, that's what I'm going to be using to determine the number of bolts that I need here to see if it's okay. Okay. So for a 5mm weld L360, I have 782 greater than 720. Fantastic. Now check the web thickness. Okay. Now I go back. We were here. And therefore, a minimum required web thickness for supporting beam, this is where we were, is 7. So this is where I get the value. Once I've chosen this, I go straight down to the table, and all of these values in this column here apply for this one here. Keep doing that. Okay, so therefore I have 7.6, and of course this is what I need. This is what, for this thickness I can go down to I can go down to 7mm, and of course we know that we have 10.5, so we have no problem. Our web thickness would be adequate in order for that weld to produce the resistance that I found on the table. Now, minimum angle thicknesses, okay? So therefore so like I said, this is just good practice, okay? So if I have a weld size of 5mm, and therefore the angle thickness should be at least 6.7mm. Now, do I have 6.7mm? No. If I go to the tables, I notice that the closest one that has at least 6.7mm will be 7.9mm, and of course that's what I would specify for the thickness of the angles. Now, for the outstanding legs, okay? So in other words, we are here on this side, the outstanding legs, and we said we had 310, I'm sorry, we had 390. So therefore we wanted to use 3/4 inch bolts, and here we go. So we have 790. So we have 5 bolts, 790, which is greater than our VF force. Okay, so for 390mm, that's why once you've established the length of the angle on one side, you have to use the same length on the other side. You just want to make sure that 5 3/4 inch bolts, the threads included, provides a capacity of 790. I need 720, I'm okay. Now, minimum thickness of the framing angles, okay? So therefore, oh yeah, I should go back to the table. Where do I get that? I get that at the bottom of the table. Minimum thickness of the framing angles is 6.9, okay? 6.9, therefore I can go down as low as 6.3. And of course, since I'm using a 7.9, I have absolutely no problem. And then last, okay. So this is the minimum, okay, minimum thickness of the supporting column, okay. Oh, sorry, last viewed. Okay, so the required minimum thickness, okay, 16. Where did I go back to? Oh, yeah, that was just so, I think this was, yeah, that was just show you that that's what we picked. Last viewed. So, and of course we need to, so here, we were here, okay. So minimum thickness of supporting member, okay, we had so it's 3.9mm, that's where we get the value, right down there. Last viewed, and therefore 3.9, of course, I'm sorry, 7.72 divided by 2 is 3.9, and therefore I happen to have the web member is 6.4, I'm okay for that. And now the sketch, okay? So here you go. So here you are welding. Here you are welding, okay, the web to your framing angles, okay? And then you are bolting to the column, okay? Now, like I said, why would you want to do this? Well, because sometimes you might want to you might have beams back to back, and you're actually framing into the, and then of course, all you have to check is to make sure that the total here, which is 76 plus 76 plus 10.5, that the total distance here is less than your T value, and you know that that's going to fit right in between the 2 flanges of your column. So in theory, you shouldn't have a problem. And that's it. And of course, you specify the size of your angles, specify the diameter of your bolts, and of course, the strength of your bolts, and always specify the strength of the electrode and the strength of the steel that you use to design your connection. And that should be your specification. So this is very similar to what we did before, except now it's the other way around. We are welding the web, bolting to the supporting member, and then the other one we bolted to the web and we welded the supporting member. Now we're going to do one very quickly, and this I'm doing this more for your general information. This is done, but it's done very rarely. This is bolted to bolted. In other words, bolted, bolted, okay? And this is where you have two beams back to back that are going to be supported on a girder. And I just want to show you what a little detail that you provide for when that's the case, okay? So here what we have is design a double angle bearing connection of a W360 by 33. So we have a W360 by 33. Okay, that is simply supported with a span of 8 meters. Okay, so 8 meters. 8 meter span, W360 by 33. Frame on both sides of a W460. So in other words, what's happening here is that this is my girder. I have a beam coming in here. I have a beam coming in there. I can probably have, okay, so therefore this is my girder. This is my W460 by 60, and these are my W360s by 33, and they're both framing on both sides of this girder, okay? And of course, like I said, that is a typical layout when you have a girder and then you have like a third of the span, a third of the span. Okay, that's a very typical framing for a floor, especially when you have large spans, a beam girder. Okay, so that's, now the angles are supposed to be bolted to the beam and bolted to both sides of the girder. So here we're gonna bolt. Everything's gonna be bolted, okay? The threads of the bolts are to be included in the shear planes, again, like I said, and I'm gonna use a 76 millimeter, okay? Show your final results on a sketch. So we're gonna go look for the geometry of a W360 by 33, and of course, the web thickness is 5.8, okay? That's what I need to know from here. So 5.8, and then of course I want to go find the web thickness of that girder, and therefore the web thickness of a W460 by 60, 8.8 millimeters thick. That's good to know. Now, what I want to know is I want to know how much of a load will a W360 by 33 actually carry. So I go to a W360 by 33. And it had a span of 8 meters. It should be very small. There it is, okay? So we had an 8 meter span, and this is a W360 by 33, so it's 168, very little, not a lot of load, because it's got a large span. So that's gonna be, so there you go. The total factor load is a W, so 168, and of course half would go on one side, half, therefore my VF value is very, well, relatively small, 84 kilonewtons. So that's what I'm gonna be designing for. Now, so here, I said 3/4 inch bolts, okay, and therefore, now my beam happens to fall here, okay. I know that this VR value is ample, but I'm not even going to use that. I'm going to go based on the geometry that I'm going to go for a much higher VR value, okay? And therefore, instead of putting like, because my beam is greater than this, so therefore I'm going to go up to, I'm going to put it in between this, and I don't care if I have 474, I only need 64. As far as the geometry goes, good practice means I should be using this as my connection, and that's what I will be doing. So therefore, I would put vertical line of 3/4 inch bolts. I know I have 447. I knew that 2 would be ample, but because of the geometry, because they suggest that this beam should be in between for these sizes, and I'm not within the first one, I will go to the second line. So that's why sometimes, guys, geometry will dictate your resistance and not necessarily the forces. And I purposely did this so to make you understand that who cares if I have way about 5 times or almost 6 times what I need. I really don't care, but at least I know that in proportion, everything is done correctly. So now check web thickness, and of course here, if I go back down to the web thickness that I need, if I go down here, I need 7.7. Wow. And if I prorate that value right now, 7.7, I only need 1.4 millimeters of thickness in order to get 84, which is ample, and I have 5.8, not a problem. So my web, okay, because if you wouldn't have prorated, you see you need a 7.7. Oh, you say, oh, I only have 5.8. I have a problem. No, you don't have a problem, because if you prorate the value of VR based on the actual thickness that you have, what you need is a minimum of 1.4, and you're providing 5.8. So that means that your actual resistance is somewhere between these two values. Okay, that's what that means. And now the minimum thickness of angles 6.9. Also, I got that at the bottom of the table. Okay. 6.9, this is the minimum size of angles here. And then again, I prorate it. So, wow, I need 1.2 millimeter thick angles. So what I'm going to do is I'm going to be realistic. Okay, I'm going to go get something that, okay, 102 by 76. I don't know where I went to. So 102 by 76. And of course, I go thick. I will take the thinnest one here. Last viewed. Now, the total reaction on the girder, of course, is twice. In other words, I have, you know, like you got to keep in mind, here's my girder like this. Okay. The beam is coming into here like this. The beam is coming into here like this. Therefore, on the girder itself is I get 84 from this side, 84 from that side. Therefore, on the girder itself, I end up getting 168. Okay. So that's what you have to keep in mind. And of course, so again, okay, if we happen to, so we get the value. Okay, so for an angle of 230 with 3 vertical lines of bolts, it's exactly the same VR value. It doesn't change whether it's I'm bolting 3 and 3. Okay, so therefore I have 478, 474. I need 168. I have ample. Now, of course, for beams connected on both sides of supported member, the bolted capacity is double that listed in the table. Okay. One bolt will be eliminated for the erection of the beam. Now, this is why I'm going to explain this, is that when you're framing these things, okay, I'm going to show you what you're going to be doing is that you're actually going to be cutting out one of the angles so that when you frame one beam on one side, you can put the bolt and it won't interfere with the beam that you're erecting on the other side. So therefore, you're going to be counting only on 5 bolts, okay? So therefore, I will only have 5 of the 6 bolts, okay? Times 2 because I have double shear here. Okay, I have double shear here, and therefore I end up with, which is much greater than what I need. Now the minimum required thickness of the girder, again, go down to the table, we get a value of 7.7. I'll go there and go get it for you. Okay, so here it is. Okay, 7.7, the same value as we had before because we are exactly in the same column, 7.7. Last viewed. So, and then of course I can go all the way down to 1.2, and I know I have a thickness of 10.2. I got that at the very beginning, so I'm okay for the thickness of the web. In other words, that means I'll have sufficient bearing. And now your final sketch. Okay, so here you go. So now you'll notice here. Okay, so I like this example, and I'm giving you this more for your general information, guys. This not you're gonna have one or the other two problems on the test, not this one. But here what I want to show you is that, remember the other example, the very first one, we coop the beam down here, okay? Well, in this one here, you would coop the beam up here, and the coop would be, make sure that you can actually be able to butt this beam into this connection so that it doesn't interfere here. So here to show you, you can coop a beam at the bottom, you can coop a beam at the top. That's number one. Number two, when I'm putting these beams together, you got to remember, I only have one crane, and the crane basically picks up one piece at a time, okay? So if I decide, for example, if I decide to connect like in plan view, okay, here's my girder, okay, here's my beam, here's my girder, and here's my beam, okay? So in plan view, if I decide to erect this beam first, well, when I come and put the connection here, I'm gonna have to put something to hold it there temporarily. So normally I will put one bolt in this connection here, one bolt in this connection here, and leave it there so it holds the beam temporarily, so that when I come and put this beam beside it and then I start putting the bolts across, the bolt head that I put here will not interfere with this angle here. So what you do is you cut out the angle where the bolt that you're going to be using to hold the first beam in place, so that when you put the next beam in place to be able to put all the other 5 bolts and connect them together back to back, well, that's what the typical erection connection you have for this situation only, okay? And I'm showing this example more for your general information, and if you guys can't follow it, don't worry about it. But if ever you guys are interested in knowing how to do it, you just go back, review it a little bit more carefully. And if it's still not clear, I'll be more than happy to review it with you. And I think that's it. Hold on a second, clear. Yeah, so guys, last assignment next week, okay? And as far as the lectures go, I think that's it, the end. So escape. So let me stop sharing. Let me put this on pause.